Hello, everybody. I am going to make some new slides for you, and I'm going to share my screen, and then I'm going to look at these new slides. All right, so welcome, everybody. And I heard that people are having troubles with this theorem, and I thought maybe, I don't really know, but I thought maybe the trouble they were having isn't so much with the proof, but with the statement of the theorem. So I've made new slides to state the theorem more clearly. All right, so what we're doing is we're doing machine learning. We're training we're training a neural net using our training data, and we want to say, can it generalize to things that we've never seen before? So the game is you randomly choose your training data, and then you find a good machine, right? So the orange dots are the training data, the XY information. The green curve is what the machine computes. We find some machine that does well on the training data, but there's a caveat. We condition what we're doing is that we find a machine that does well without simply memorizing the training data. And by that, to be a little bit more formal here, we're saying the number of bits to describe the machine has to be much less than the number of training data items, right? So it can't simply memorize. And then we can prove that with high probability, the same machine that we learned from works well on instances that it's never seen before, right? So this seems very surprising. How can you expect it to learn to give the right answer on an image it's never seen before? All right, so let's go through the theorem a little deeper and make sure that you can at least understand what believe that the theorem is true. All right, so before we go on, I teach a course in logic, which you might want to look over. And in it, I informally talk about relate for all exist statements to a game. And basically, whenever you want to prove for all x, how would you prove it? You might say, let x be an arbitrary value. But to give us some personalities, let's say that there's some adversary who is trying to hurt us, and he gives us the value x. Similarly, if we're trying to prove there exists a y, then the prover gets to construct this y. Now let's add, suppose that there's some objects that are chosen randomly. And then how do we get those? Well, we flip coins to get those. And so once we have all our objects, then we have to prove that the statement is true for the objects in question. Oh, also, the order in which the players go matters a great deal, and they have to go. They read the expression left to right. All right, so here's just if you want to see more about what I'm talking about. All right, so let's state this whole game as this whole theorem is a game between these players. The adversary, what does he do? Well, he first gets to decide what our universe is. He gets to decide the all the possible XY pairs that might come up, right, in our universe. Now, here X he gets to decide what the computational problem is. So just as an example, X might be an image of a cat, and then Y is the label cat, and that's the problem we're trying to learn. Given X, we're trying to learn what? We're trying to learn Y. All right, so what is it that the adversary is providing? It's providing kind of the universe of these things. So I think of the universe as kind of like a black box vending machine. Here's a vending machine. And what happens is you put a quarter into the vending machine and out comes a random pair, X, Y. It selects a random pair. And that random pair is chosen randomly using our dice, right? So when the adversary is choosing our universe U, what in fact is the adversary choosing? Well, it's choosing for every possible XY pair. Um, it, it, the adversary provides a real number, P of XY, PXY, such that it gives the probability that this XY pair comes out, right? So it's a distribution. So the sum of these probabilities have to be 1, and they all have to be between 0 and 1, right? So this is a distribution that the adversary gets to choose. All right. Then the adversary gets to choose various parameters. D, the number of training data, N, the size of the machine, epsilon, some infinitesimal, small little amount. Well, actually, the theorem works if epsilon was even a half, but all right. So, but the requirement is this relationship, and it basically says that the complexity of the machine is less than the amount of training data. All right, so then it gets to choose some family of neural nets, right? So the adversary, who's our worst case, trying to make our life harder for us, even gets to design what the machines look like. Why do we let the adversary do this? As well, because we want the theorem to be true, a big for all in front. We want the theorem to be true no matter what your universe of X and Y's look like, no matter what your machines look like, right? So the adversary gets to choose these machines. And the only restriction is that the number of these machines is limited. And the way we restrict the number of these machines is we say that they're described by M bits, right? If you want to specify one of these machines, you use little m bits to specify which machine we're talking about. All right, so that's what the adversary does. And all right, so why are we restricting our machine, right? We're going to see here, we say m has to be small, and that restricts how complex, how many variety the machine can be, right? Well, you might say each machine might be very complex, but there can't be very many different machines, so it can't learn as many different things. And one of the things that restricts us is it can't just memorize the answers, right? Because the way you learn is by choosing one of these machines. And as we've seen in the compression slides, if you don't have a lot of bits to describe the machine, it can't memorize the answers, right? And of course, the problem with memorizing the answers is that it causes what we call overfitting. All right, now instead, the machine somehow has to take these D training data and compress them into M bits, as we've seen. And when it does so, it forces it, hopefully, to learn the data, and so that maybe you can generalize. All right, so that's why we're restricting it here. We've seen that motivation before. All right, so now what does the prover do? It has these machines. The prover gets to, well, the prover's not doing it. The dice are proving it. Here we have the dice are not the dice, the coins are flipping. And here we come. They're coming out of the machine. The prover chooses his D data pairs, right? And so here, and where does this data set come from? They're assumed to be chosen independently at random from the universe, right? And so the adversary doesn't get to choose these, right? The adversary chooses the distribution. The adversary doesn't choose what the items will be. They're chosen randomly from that distribution, right? All right, and then we're assuming that the prover is able to find from the set of all machines, right? Can find a set of the weights so that the machine can find a machine such that it gets the right answer on all but some epsilon double primes and purple epsilon fraction of the training data, right? So it does well. It gets the right answer on all the training data except for some small fraction of them. And I changed the notation actually to M star, but we'll see that probably in a minute. Right, so this machine does well on the training data, right? So this is just a repeat. This machine here is chosen to be one of the machines from our set, so that on this large number of training pairs, the answer is the required answer, right? All right, so here is where all right, so the adversary comes up and he says, well, actually, the prover doesn't completely get to choose the machine in question. The prover is going to, the adversary gets to, if there are a number of machines from the set with the same property, then the prover gets to choose which one is the adversary gets to choose which one of these is going to be grabbed by the prover. All right, let's go on here. Now the prover now has a machine, and it's like Google's finished training, and now the car is going to drive out into the world to not want to kill your grandmother, right? So here it's going to choose a new random XY pair from the same distribution from the universe, and then the prover notes, hey, what it wants is that the same machine here. Remember, I told you I changed the name of the machine that we chose into M star. He just notes whether M star works, meaning if you give M star X star, does it output Y star, right? That's what we want. We want it to work on the new randomly chosen data pair that we've never seen before. All right, so that was just one experiment, and the prover is going to repeat this experiment many, many, many times. Like, let's call it an infinite number of times. And every time it uses independent coin flips. And remember what it's choosing. It's randomly choosing the data set, the training data, and then given the training data, it's choosing our selected machine. And then once it has a machine, it randomly chooses some new unseen piece of data, and we count whether or not we see how many times this experiment succeeds by having the machine give the right answer on the training data, right? And what we're going to prove is that this experiment succeeds, that this machine does give the right answer for at least this purple epsilon plus the red epsilon fraction of these experiments. Remember, the red epsilon was how small n was compared to d, and the purple epsilon was how well our machine M star does on the training data. Right, so the statement is that with high probability, our trained machine does well on the new data it's never seen before. All right, so this seems really hard to believe, and so let's argue. The adversary is going to argue why it can't be true, and the prover will argue why it is true. Right? So the adversary says, "Surely I can mess you up. How will I mess you up? First, let the new training data that we've never seen before be some really crazy image, right? How do you expect the machine to recognize that this is a bicycle? You know, I can barely recognize this is a bicycle, right? So that's how the adversary can make the problem hard. Well, worse, maybe this new training data that it's never seen before actually is told it has the wrong answer, right? Maybe the machine's going to be given this crazy image of bananas and expect it to recognize it as a cat, right? How do we prevent this from happening? Well, the prover comes back and says, no, sorry, you can't do that. Why can't you? Because the adversary has to specify, right, this universe, this distribution, this black box at the beginning of the game, right? It's the very first thing he does. And the training data and the data we've never seen before are randomly chosen from this exact same distribution, right? So he can't make the training data different than the data he's never seen before, right? They're different, but they're chosen from the same distribution, right? In fact, if the adversary puts this training data in the distribution, right, where you have a picture of banana bike and the answer expected is to be cat, then the prover is just as likely to choose this example as its training data to learn from as it is to use it as test data, right? So that's the key idea here. All right, but then the adversary says, yeah, okay, great. You're not going to let me change this distribution, but I also get to choose the neural networks, and I can make this neural network that you're using to be so bad that it can't compute anything, right? Again, the prover comes back and says, yeah, you get to choose the family of machines. It's true. But remember, I do get to choose the machine in star that works sort of best or reasonably well from this family. And the problem is that if this family of machines is bad, then the prover won't be able to find a machine that gets the right answer on this purple fraction of the training data. Right? Remember, we said suppose that the prover was able to do this, right? Well, what happens if the prover's not able to do this? What happens if the machines are bad and none of them happen to give the right answer? None of them happen to do reasonably well in the training data. Well, the problem is this whole, about conditional probability. We're asking, what is the probability that our experiments succeed, conditioned on the fact that the prover is able to find a good machine. And if the prover isn't able to find a good machine, because there is no good machine here, then by the rules of the game, the adversary automatically loses, right? And so now the adversary is starting to realize that, hey, maybe this crazy result is true. And then you can go back to the other video and look at the proof and tell me how you're doing with it. All right. Bye.